Today we're going to take a look at the material for exam 6, my chapter 17, your chapter 19 on thermodynamics. And I think I gave you the correct review document. It should be version 2 that we're working from. And I've highlighted the ones I want to tackle. And we'll see how well I can do. I may have to refer to my work problems occasionally to get my bearings, but let's take them one at a time. Let's see. Marker. Let's look at number 2. Yeah, it's showing up. So the point of number 2 is just to emphasize the statistical nature of thermodynamics. If you have 2 flasks that are connected, like that, and you have 5 particles. What's the probability of finding all 5 particles on the left side? What's the probability of finding 1 particle? It could either be here or here. So the probability is 1/2 for 1 particle. How about 2 particles? What's the probability of finding 2 on this side? Well, the probability of that particle is either here or here. So in statistical terms, in mathematical terms, it's the product of the 2. You have an equal chance of finding this one here or here, but this one could be swapped also. Then if we have 3 particles, then you got another 1/2. 4 particles, you got another 1/2 because it's 2. And then 5 particles, you have another 1/2. So what does that mean in mathematical terms? Well, 1, 2, 3, 4, 5. It's 1/2 to the 5th power. All right, so there's 2, 4, 8, 16, 32. So let's see. Our answer's in percent. So we have to do the math on that one. What's the reciprocal of 32? Times 100 is 3.13. Like that. That's why the answer is C. All right. Let's scroll. Oops. Lock that one in place. Find my next one. Okay, number 14. Okay, for this process, and I think that's chloroform, goes from solid to liquid. And the enthalpy, the standard enthalpy is 9.19 kilojoules per mole. And the standard entropy is 43.9 joules per mole K. Notice the difference in units here. Kilojoules here, joules here. Plus we got the addition of a temperature. What's the melting point of chloroform? When it says melting point, that means that we're in an equilibrium situation. And when you're in an equilibrium situation, the Remember when we were talking about entropy of surroundings? And we could say the entropy of the surroundings is equal to negative delta H over T. And that's true. At equilibrium, we have the system in here, surroundings here. At equilibrium, the total is equal to 0. So in an equilibrium situation, which is boiling point, melting point, sublimation point, whatever the case may be, when you have both phases together, the change in entropy is balanced between the two. So if this one is minus delta H over T, this one has to be plus delta H over T in order to balance, because when you add them both together, surroundings plus system, they have to be opposite and equal. So with that knowledge, if the question is, what's the melting point? The melting point references to what's going on in here, not out here. So for this one, all we have to do is change that to the system, and that's a positive sign. And now that we have that information, we can look to the problem and see if we've got what we need. Delta S of system is 43.9 joules per mole K. And the delta H is 9.19 kilojoules. So 9.19 kilojoules, 9.19 kilojoules is 10 to the third times this is joules per mole divided by the temperature. And that temperature is the one we're after. But notice we had to make these units equal. This is in joules, this is in kilojoules, so I had to change that to joules. Now what I need to do is put the T on this side, put this one over here. So now we have 9.19 times 10 to the third divided by 43.9. And let's see what that is. So I get 209, 3 significant figures, so that's enough. But remember, that's in K. And the answer is in degrees Celsius. So what we have to do is change that to Celsius. We subtract 273. And I could have lined them up better, couldn't I? Minus 273. So 9 from 3, I have to go backwards. 9 from 3 is 4. And then 0, got 6 left over. So it's a negative 64 degrees Celsius right here. Okay? All right, let's see, that was 14. Let's find the next highlighted one. 20. Okay. In which case must a reaction be spontaneous at all temperatures? This one is using the Gibbs free energy equation. So let's see, put 20 here. So delta G is equal to delta H minus T delta S. So under what conditions is the reaction spontaneous? We learned that spontaneous reactions require that delta G is negative. So this one has to be negative in order to be spontaneous. So under what conditions would any reaction be spontaneous at all temperatures? At all temperatures means we don't have to worry about the size of these values. We just need to be sure that both of them are negative. If both are negative, then it's always negative. So for this one to be negative, delta S has to be positive at any temperature. And delta H has to be negative. So delta H is negative and delta S is positive. There it is right there. Okay? It doesn't matter what the temperature is. It will always be spontaneous. And that's the beauty of Kelvin. Right? The temperature, it's always positive with Kelvin. So we don't have to worry about that as a sign changer. Okay, that's 20, let's see, 26. When a stable diatomic molecule spontaneously forms from its atoms, what are the signs? A stable diatomic molecule spontaneously forms from its atoms. So if we have atoms of A plus atoms of B forms, diatomic molecule. Two A's yield, there we go. So this means that these are separate, and this one is actually bonded to the other one. And we formed a bond. So what are the signs? Well, let's see. How about delta H, right? What's the enthalpy of this reaction? Well, when you form a bond, you get stability. You give up energy. So we should have a negative delta H. Let's see, we've got delta H, delta S, and delta G. Okay, so if we form a bond, the diatomic molecule is more stable, which means lower energy. So we had to give up energy. When you give up energy relative to the system, that's an exothermic. You lose energy. So that one's negative. Also, it says that this is spontaneously formed. If it's spontaneously formed, we know that this one is also negative. Okay? And we're going from two atoms, more, say, random, to less random. Right? So the delta S, the randomness is decreasing, going from 2 to 1. So this one's also negative. So they're all three negative. Right here. All three of them are negative. 26. Let's see, what's the next one? I'm going to scroll this one. Let's see if I can do that with them. And here like this. There we go. All right, 31. Calculate Ksp. Okay, we're looking for the solubility product. of sodium chloride at 25 degrees. So temperature is 25 degrees C, and the salt is sodium chloride. We may not need all that, but I'm putting it up there anyway. Okay. And we're given these free energies for sodium ions, chloride ions, and sodium chloride solid. Okay, we got, this is a two-step problem. In order to determine the K value, we go back to a formula. I'm going to write it over here. Minus RT log K. Here we go. So the standard gives free energy. Excuse me, I left off. No, I got it. Minus sign. So that's what we're headed for. And we know to use this one because we're given these types of information and we're asked to calculate that. So we need to find out what is this. We already know what that is, and we know what this is. So we need to find this from that information. In order to do that, we know that the delta G for the reaction, and let's put the reaction over here, solubility product. So we're going this one. Actually, we want to put a solid there. Yeah, okay. And we're going to here plus here. Okay. So how do we calculate the delta G for that expression? We use the sum of the delta G zeros for products minus the sum of the delta G for reactants. Reactants. There we go. Yeah. So what we need now to do this is, what are the products? Well, the products are sodium ions and chloride ions. Sodium ions and chloride ions. How many are there? There's just one each. Right? So we've got the sum of this one, 262 plus 131, actually it's minus. And then minus this one, 383.8, minus a minus 383.8. Right? So this one's going to be a minus value and the other one's going to be a positive value. So let's put this one in first, 383.8. It's a positive value, right, because of that. And then 262 and 131 subtracted. And I get minus 92. So delta G 0 equals minus 92. And this is kilojoules per mole. Okay, actually, kilojoules. We've already taken the moles into account, right? Because, well, no, they're all 1 mole, 1 mole, 1 mole. The moles have already been canceled out, so this is just kilojoules. Let's see, did I do that right? No. a decimal in the wrong place. 9.2. That makes more sense. This is about 390 and that's about 380. Yeah, that's better. Okay, now that we know that value, we can plug it in this formula and find out what K is. So we've got minus 9.2 kilojoules. But what is R in terms of? Right? What are the units on R? 8.3145 minus 8.3145 is in joules. Joules per mole K, I believe. Joules per mole K. Yeah. So this one, temperature. What's the temperature? 25 plus 273 is 298. That's times 298. Okay. And that's times the log solubility product. Okay. This needs to be in joules. It's in kilojoules now. So that's 10 to the third joules. Now we can solve for this one. So what do we need? We need this one divided by that one, divided by that one. So 9.2 exponent 3. Let's change the sign. There we go. And then divided by a negative 8.3145. And then divided by 298. So that's 3.713. 3.713 equals the natural log of K. So K is equal to E to that value. Remember the anti-log? This is the anti-natural log. So the base of this log is E. So it'd be E to the X on your calculator. With that value, I just need to hit this key right here, E to the X. And that's 40 point, yeah. See, how many significant figures do I have? 2. 41. Yeah, 41. And it doesn't have any units. Remember, K's don't have units. Well, they have units, but we don't say them out loud. So here it is. K for this process, this solubility, is 41. What does that mean? It's a big number, right? 41 is a big number. So that means sodium chloride is very soluble. All right, up to 31. Let's see who's next. We're doing pretty good. 34. I'm going to have to go down here. That's good. 34. Consider the gas phase reaction. Nitrogen monoxide plus 1/2 oxygen yields nitrogen dioxide. Delta H is minus 56.91 kilojoules. K is 146 times 10 to the 6th at 25. for this system at equilibrium, how will raising the temperature affect the amount of NO present? At equilibrium. I think this is going to be pretty simple. Yeah, there's a lot of blue smoke here. And some of these things would have been useful to do some calculations. But to answer this question, what you need to do is recognize that delta H is a negative value. That means, let's just write it up here. NO plus 1/2 O2 is in equilibrium with NO2. They're all gases. Delta H is negative, which makes it exothermic. So we would add delta H on the product side, right? So how will raising the temperature affect the NO present? How will it affect that? If you increase this value, Le Chatelier says you're going to shift it back toward NO. So you're going to increase the amount of NO right here. Right? And it doesn't depend on K because it's already at equilibrium. Right? For this system at equilibrium. So who cares what K is? It's already at equilibrium. What's it going to do when we kick it? It's going to move back to the left. Okay, 34. Let's see here. 40. The second law of thermodynamics states, let's see, let's take, what's the first law say? The change in energy content of the entire universe is 0. It's fixed. It has a certain amount of energy. That's it for the whole universe. The second law, let's see, this is the first law. The second law refers to entropy. So what happens to the entropy of the universe what happens to the entropy of the universe for any spontaneous process is positive. It's always increasing. So let's see. Nope, energy conserved, that's the first law. Entropy of the universe increases during a spontaneous process, that's it. Alrighty then, that's 40. $42. Let me get my bearings here. Just so I don't step on my own tongue. 42. A mixture of hydrogen and chlorine remains unreacted until it's exposed to ultraviolet light from a burning magnesium strip. Then the following reaction occurs very rapidly. Hydrogen and chlorine gas combine to make hydrogen chloride gas. Okay. We've got some information in here, right? That says it's spontaneous. That says it's exothermic. And that says the entropy of the reaction decreases from here to here. So what that means is we can't deduce the entropy from the number of gas molecules. Right? Going from 2 to 2 doesn't tell us anything. This tells us definitely that it is negative delta S for this. It's more ordered. Well, actually, that makes sense. right? You got these two separate, and then you got this one. Okay, so it does it does comply with what we would expect. Less ordered, more ordered, negative delta S. Okay, but that's not the question. Which of the following is consistent with this information? Okay, the reactants are thermodynamically more stable than the products. Thermodynamically more stable than the products. Well, actually, I would expect that to be true. Oh, I think I misread that. No. I did misread it. The reactants are not thermodynamically more stable because it's exothermic. Thermodynamic stability would be, and there's less energy in here than there is there. So the energy level has decreased, and that adds to stability. So this is a false statement. It's the other way around. The products are more stable. Also, because it's spontaneous, that indicates there's more stability. The reaction has a small equilibrium constant. A small equilibrium constant. If we actually calculate the equilibrium constant from the same formula that we used before, what would that be? Well, let's see, delta G is, and we have to convert that to joules, minus 45.54 times 10 to the third minus R, which is 8.3145. Temperature is, what is the temperature? We have to assume that it's standard. So it'll be 298. And then log K. So if we actually calculate that, 45.54, change that sign, exponent 3, and then 8.3145, and then 298 divided into that is 18.38 equals the log of K. So K is now equal to e to that power. All right, so I just need to get that P again. K is equal to 9.6 times 10 to the 7th. That's a pretty big K. And actually, your K is going to be positive. Anytime delta G is negative, it's going to be greater than 1. So it's not a small equilibrium constant, it's a large one. The ultraviolet light raises the temperature of the system and makes the reaction more favorable. No, the ultraviolet light provides the activation energy. Right? Let's see. These gases are contained in a bubble, in a glass ball. We light the magnesium strip outside the bubble, not inside. So it's just the light that gets through that sparks the reaction. So that's activation energy. So this one's false. It does nothing to the temperature. The negative value of delta S slows down the reaction. Slows down the reaction. Oh, no. What are we talking about when we say slows down or speeds up? That's kinetics. Thermodynamics has nothing to say about kinetics. Nothing whatsoever. So saying anything relative to rate of reaction here is false. It doesn't matter what the rest of the statement is, it's false. We're talking about before and after. We don't care what happens in between. In between is where the kinetics occurs. Okay, so by process of elimination, this one should be true. The reaction is spontaneous, yes, but the reactants are kinetically stable. The reactants are kinetically stable. I just said you can't say anything about kinetics, didn't I? All right. We're going to stretch here. We can say they're kinetically stable because we had to supply the activation energy. So if we're going to do an energy diagram where we go like this, like that, this is the activation energy here. We had to supply the activation energy by ultraviolet light. They were stable, happy right over here until we kicked them with ultraviolet. So they were kinetically stable to begin with. That's the interpretation of that answer. All right. So that was 42. Let's see. 52. I'm going to have to do some cursor work here. There we go. 52. See, I better stop that thing from moving around. 52. Okay. We need the review document and useful information. Okay. This plot, log K against 1 over T, is referencing this equation here. Natural log K equals minus enthalpy over R times 1 over T plus, let's see, I can stay on the board if I write small, delta S0 over R. Yeah, it's still on the board. Okay, so this plot says this one is Y axis, this one is X axis, this one is the slope, and this one is the Y intercept. Okay? So that being said, let's see, 52. Thought I had it right. Yeah, there we go. Let's look at the question. The equilibrium constant of a certain reaction was measured at various temperatures to give the following plot. Okay. This versus temperature. Actually, inverse temperature and natural log. Okay. What's the delta S for the reaction? The delta S refers to the y-intercept. The y-intercept is 3.0. 3.0 equals the log K. Okay, but that's also equal to delta S0 over R. Okay. So we're not solving for K. We're solving for delta S0. So that means we need to plug in this value, which is 8.3145 multiply that times 3, and that should give us our answer. Let's see, how many significant figures? Just 2. So that's 25. Delta S 0 equals 25 joules per mole K. There it is, right there. Okay, so this is an exercise in graph interpretation. You have to know what that means, and it's derived from this formula. This equation, I should say. Okay, 52. And let's see how far along I can get before I have to cut out. 56. The equilibrium constant Kp in atmospheres. So now we're looking at equilibrium constant that was derived from partial pressure. For the dissociation reaction, chlorine gas to 2 chlorine atoms was measured as a function of temperature. A graph of log Kp versus 1 over T for this reaction gives a straight line with a slope of minus 1.651 times 10 to the 4th and an intercept of 14.51. Value of delta H for this dissociation. So it's that same formula again, only we're using a different part of it. Let's see. Negative delta H over R. That's equal to the slope. And the slope of the line is minus 1.651 times 10 to the 4th. So this one's going to be 8.3145. And we just need to multiply this one times that one and change the sign. Just eliminate that negative sign, and that will give us our delta H. 1.651 exponent 4. 8.3145. So I get 1.373 times 10 to the 5th joules per mole. Okay? But the answers are in kilojoules. Okay. So how many kilojoules is this? Well, take 3 out of there. Okay. So we take 10 to the 3rd out of here and put it right there. So that means 1.373 times 10 squared kilojoules, or 137 kilojoules. Right there. Okay? 56. What am I doing on time? Got a few more minutes. If I'm lucky, we might be able to finish this ahead of time. Let's see. I need to scroll this one a little bit. There we go. All right, 57. For a certain process at 300 K, the temperature is 300 K, delta G. Now this is the actual delta G for that reaction, not the standard. It doesn't have a little 0 up there. Is minus 12.2 kilojoules. Delta H is minus 7 kilojoules. If the process is carried out so that no useful work is performed, delta G is what? If work is 0, what is delta G? Delta G equals what? Put my thinking cap on here. Oh, yeah. If the process is carried out so that no useful work is performed, delta G is. Actually, that doesn't matter because the maximum available work is related to delta G, that formula. Right? So this is equal to, that doesn't matter really. That's blue smoke. The delta G is still minus 12.2 kilojoules. Okay? That's a trick question. No doubt about it. All the rest of that stuff was unnecessary information. Let's see. Oh, we're done. Those are the only ones that I had marked off. Okay. Y'all got any questions? Let's see. So we'll have an exam on this chapter next week. And that's the review for today, exam next week. And then we'll introduce the last chapter, electrochemistry, which is chapter 20 in your book, in Brown. And there won't be a lab, but hopefully I'll have, I'll hand out the hard copy for our last lab, which will be the following week. And that, we'll have a review on that. Yeah, 2 weeks from today, we'll have a review. And then our last exam will be on May 13th.